Good afternoon, everyone. This is me, Ashwani, here with yet another part of chemistry, chapter 1 of plus 2, that is solutions. So, we have already completed two parts in this chapter 2 from this chapter 1 of plus 2. And last day, in our last class, we have discussed about vapor pressure and the effect of temperature on vapor pressure towards the uh, end of the part 2. Okay. So before starting today's class, I just wanted to tell you that there is a scholarship for the students of graduation and post graduation. If you're planning to opt BSc Physics or BSc Chemistry or BSc Maths or any other streams of science, okay? If you're planning to opt such subjects and if you're going for graduation in that particular subject, you will have a scholarship named Inspire Scholarship, which is actually a scholarship in India, which is the largest funding scholarship. Okay, it is providing around 2 lakhs to UG students and 2 lakhs to PG students. So the thing you have to do is that you need to score the maximum marks in plus one and plus two. When I was in plus one and plus two, and when I went for the graduation, in those days, okay, years back, in those days, the cutoff for Kerala was 99 percentage. So as to enter or so as to get selection to Inspire Scholarship, the cutoff was 99 percentage because that Kerala is a state with high literacy rate. Therefore, the cutoff will be high. Okay, will be higher than other states. So I had in those days I had a cutoff of 99 percentage, and I had 99.5 percentage in my higher secondary in plus one and plus two, so that I was easily I got an easy selection to Inspire Scholarship. So what you have to do is that, as I already said, you need to score maximum marks in the science subjects in plus one and plus two, so that you will get an easy selection to Inspire Scholarship. It's really great to achieve in your younger ages. In 17, 18, 19, 20, you can earn lakhs and lakhs through Inspire Scholarship. Okay. I don't think other scholarships provide as much as the amount provided by Inspire Scholarship. As I already said, it's providing 2 lakhs to UG students and PG students. But the thing is that you need to fall under the cutoff category provided for each state by the Inspire team. Okay. So keep that in mind. When I was in school, nobody told me about such a scholarship, and I was totally unaware about that till I entered college. So I made sure that you all know about the scholarship so that you can work on this. You can work on getting this achieving Inspire Scholarship from now onwards. Okay, study well. Okay, let's start today's class. We already discussed what is vapor pressure in our previous class. What is vapor pressure? What is vapor pressure? I'm taking a container. I'm taking few amount of volatile liquid. What is volatile liquid? Volatile liquid. Liquids which can easily vaporize. They are called volatile liquids. They can evaporate and go fast, okay? Or they have high escaping tendency. They can vaporize easily. Such liquids are called volatile liquids. So I took a volatile liquid in a container. I closed it. Okay, I closed it. Then the vapors of volatile liquids, vapors are filled here, filled above this liquid surface. This vapors this vapor of volatile liquid is exerting a pressure on the liquid surface, and that pressure is called vapor pressure. Hope you understood. I'm taking a volatile liquid in a container. I'm closing the container. The vapors of volatile liquid is filled throughout the container above the liquid surface. The vapor is exerting a pressure on the liquid surface, and that pressure is called vapor pressure. And I've already told you the relation between vapor pressure and temperature. As temperature increases, the kinetic energy of molecules increases, and hence, therefore, vapor pressure of the particular liquid increases, particular volatile liquid increases. Today, we are going to learn two laws, which are those laws are very easy. Dalton's law and Rawls law, very, 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 very easy laws in plus two chemistry. But many students are saying that, ma'am, these two laws are really difficult. I don't know why. I don't know why these kids are saying like this. Because these laws are really easy. The thing is that you approach these laws in a difficult manner so that the laws are really difficult for you guys. So let's approach these laws in an easier manner. Okay, come with me. Come along. I'm taking a container here having volatile liquid A. Volatile liquid A. I'm taking another container here having volatile liquid B. I'm taking one more container here and I'm mixing both liquids, okay? A and B. I'm mixing both volatile liquids. A, then B. Sorry, A, the color of A was different, and B. Fine. What is the vapor pressure of this volatile liquid in A? Container A. In the container A, I've already said there is a volatile liquid. What is the vapor pressure of the volatile liquid in container A? Tell me. You need to remember that it's a pure component. Okay? The container has only volatile liquid A. No other volatile liquids are present in the container. In that state, we have pure component of A. As no other volatile liquids are mixed with A, we have pure component of A. If it is a pure component of A, how do we represent the partial pressure or the vapor pressure of A? It is P naught A. Yes, P naught A. And in the second container B, have pure component of volatile liquid B. Pure component of volatile liquid B, and the vapor pressure can be denoted as P naught B. Fine. In the third container, I have mixed two volatile liquids, A and B. The total pressure of the solution, the total pressure or the pressure of solution, vapor pressure of solution or the vapor pressure, total vapor pressure is equal to sum of those pressures of volatile liquids, sum of A and sum of B. Sure. Is it P naught A and P naught B? P naught A plus P naught B? What I have told you, P naught A is the vapor pressure of pure component of A and P naught B is a vapor pressure of pure component of B. But in third container I have mixed A and B. So it is not a pure component anymore. It has been mixed. So how do we represent it? PA, it is PA plus PB. Partial pressure of A plus partial pressure of B. Clear? Partial pressure of A plus partial pressure of B, as it is not a pure component anymore because it's mixed. It has been mixed. Fine. This is the law itself. You have already learned the law. That's just Dalton's law, man. According to Dalton's law, see the theory provided here, theorem provided here. According to Dalton's law of partial pressure, the total pressure over the solution in a container. The container is here. Container is in red color. And the total pressure of the solution, PT, the total pressure of solution, PT or PS, total pressure of solution is PS or total pressure PT is equal to, will be the sum of partial pressures of individual components. The total pressure of a solution in a container is equal to the sum of the pressures of individual components. Is that clear to you? If I've taken a container and I've mixed two volatile liquids or mixed any liquid, any two liquids, the total pressure of that solution, okay, when I mix two liquids, it is a solution thereafter, right? So the total pressure of that solution will be equal to the pressure of individual component, A and B. Pressure of A plus pressure of B gives the total pressure of the solution, and this is a Dalton's law. Very simple. Now, shall we move to the Rawls law? Move on to Rawls law. So as to know Rawls law very easily, we should have a base from Dalton's law as well. Let's take a container. I've mixed A plus B. Okay, A is here. A is a volatile liquid. B is a volatile liquid. I've mixed two liquids, and the partial pressure of A is PA. Partial pressure of second component B is PB. According to Rawls' law, the partial pressure of A is directly proportional to mole fraction of A in that solution. I've taken two volatile liquids, say A and B, I've mixed it in a container, and the partial pressure of A is directly proportional to the mole fraction of A in that solution. This is what Rawls' law says. And the partial pressure of B is directly proportional to mole fraction of B. Shall we remove the proportionality and give a proportionality constant there? PA equal to PB equal to, the proportionality constant I'm giving is P naught A and chi A, mole fraction of A. Here I'm giving the proportionality constant of P naught B, chi B. Fine? Fine, fine, fine. I've said, according to Rawls law, the partial pressure of individual components when two volatile liquids are mixed, made into a solution, the partial pressure of individual component is directly proportional to mole fraction. Partial pressure of individual component A directly proportional to the mole fraction of A. Removing the proportionality, I've given a proportionality constant, that is P naught A. Here, partial pressure of B directly proportional to the mole fraction of B. Removing the proportionality, I've given a proportionality constant P naught B. What is PA? Partial pressure of the component in a solution. What is P naught A? P naught A or P naught B? Just PA or just PB is actually the partial pressure of the component in a solution. What is P naught A? The partial pressure or the vapor pressure of pure component. P naught A or P naught B. It is a vapor pressure of pure component. PB and PA means the pressure of the component in a solution after it's mixed. Fine. So this is Rawls law, and we need to have a derivation from Rawls law and substitute it in Dalton's law's equation. As per Dalton's law, we already learned that P total equal to PA plus PB. The total vapor pressure of a solution is equal to the sum of individual vapor pressures. Right? Individual vapor pressure of A plus vapor pressure of B gives the total vapor pressure of the solution. Substitute the equation we got from Rawls law in it. According to Rawls law, we learned that PA equal to P naught A chi A or mole fraction of A. PB equal to P naught B chi B, the mole fraction of B. So substitute these two values here. Fine. Hence we get PA equal to P naught A chi A plus P naught B chi B. Now, we have a relation XA, XB. The sum gives 1. Mole fraction of two components in a solution is always 1. Keep this in mind. Mole fraction of two components in a solution is always 1. From this, we can say that P naught A, substitute for chi A from this value. Chi A is 1 minus chi B, taking chi B to the right hand side. 1 minus chi B plus P naught B chi B. Just rearrange P naught A plus chi B. Taking chi B outside, we have P naught B minus P naught A. This is the equation to find total vapor pressure. Total vapor pressure, PT. Total vapor pressure, PT. So you might get few numerical problems asking to find the total vapor pressure of a solution. So you need to find PT by using the equation P naught A plus chi B into P naught B minus P naught A. The same derivation is given here with 1 and 2 instead of A and B. P naught 1 plus P naught 2 minus P naught 1 into chi 2. To find the total vapor pressure, you need to use this equation. There is one more equation you need to know so as to do the problems. PA, partial pressure of a component, equal to P naught A chi A. You know this equation, right? Using this equation, we can find what? We can find the partial pressure of a component. Using this equation, we can find the partial pressure of a component PA. The partial pressure of a component PA. Fine. There is also another equation to be kept in your mind, that is YA equal to PA by P naught A, or YB equal to PB by P naught B. YA and YB means the mole fraction of that particular component in vapor phase. The mole fraction in vapor phase. Questions can come like this. Find the mole fraction of a component in vapor phase. What do you have to do? Just substitute the values in this particular equation, Pa by P naught A. P naught A will be given in the question itself, and from where will you be able to find Pa? Pa, the equation for Pa is here. Pa equal to P naught A chi A. You can find the value of Pa by substituting the values for P naught A and chi A, because the equation for Pa is P naught A chi A. Okay, substitute the values for Pa. In Pa by P naught A, you'll get the mole fraction of a substance in its vapor phase. That is Ya or Yb. Clear? With the knowledge you have acquired from this, shall we do a problem? Shall we do a numerical problem? This is the same question from NCERT. Okay, as our sessions also focus the students of NCERT and SCERT. Fine. Vapor pressure of chloroform and dichloromethane is given at a constant temperature. It is 200 and 415. We are asked to find the vapor pressure of the solution. Vapor pressure of the solution. So as to find the vapor pressure of the solution, that is P total. What is the equation? See the equation. P1 naught plus P2 naught minus P1 naught into chi2. P1 naught plus P2 naught minus P1 naught into chi2. Okay, that is the vapor pressure of pure component of 1, vapor pressure of pure component of 2, vapor pressure of pure component of 1, and the mole fraction of second component. P1 naught and P2 naught is already given in the question, 200 and 415 respectively. What we have to find is chi2. Chi2 means the mole fraction of second component. So as to find chi2, there is a mole fraction of second component. We need to find the number of moles of second component divided by number of moles of first component divided by plus number of moles of second component. Fine. Substituting this here, substituting the value of chi2 here, we'll be able to find P total. Okay. Next, the second question is mole fraction in vapor phase. We need to find the mole fraction in vapor phase. So as to find the mole fraction in vapor phase, the equation used is Ya equal to Pa divided by P naught A. P naught A is already given in the question, that is 200. 200. Pa should be found out, right? Pa equal to chi A into P naught A. P naught A is already given. We just have to find chi A. How to find chi A? Chi A equal to number of moles of A divided by number of moles of A plus number of moles of B. Substitute this value here. We'll get Pa. The value of Pa should be substituted here. We'll get Ya. All set? The methods to reach the answer, the route to reach the answer have been given to you. I have given the route to reach the answer, the method. You just have to find it and substitute in the equations which I have provided to you. Now we are moving on to other topic, ideal solutions and non-ideal solutions. Ideal solutions means just simple topic, because ideal solutions are the solutions which obey Raoult's law. Okay, which obey Raoult's law over a range of concentration. Fine. Obey Raoult's law means, according to Raoult's law, we know that Pa equal to P naught A chi A. According to Raoult's law, we know that Pb equal to P naught B chi B. And again, according to Raoult's law, we know that Pa plus Pb equal to P naught A chi A plus P naught B and chi B. If these equations are obeyed by a solution, it's called ideal solution. Okay, ideal solutions are those solutions which obey Raoult's law. In your school, there might be students like, okay, obedient students. They'll remind teacher about the test papers. They'll remind teacher about the homeworks. Okay, they're always on time, or they're always in time to the class. They'll never be late. They'll score good marks, right? Obedient students with specs like mine. Okay, so such students obey teachers, right? The same way, those solutions which obey Raoult's law over a range of concentration is called ideal solution. Okay, as per the Raoult's law, we have Pa equal to P naught A chi A, Pb equal to P naught B chi B, and Pa plus Pb equal to P naught A chi A plus P naught B chi B. So, those solutions which obey these equations, they are called ideal solution. Also, Those equations whose enthalpy of mixing and volume of mixing is equal to 0, such solutions are called ideal solutions. What is enthalpy of mixing? When two components mix, there will be some, like in some cases, energy will be released. In some cases, the energy will be absorbed when two components mix. So that is called enthalpy of mixing. And volume of mixing means the change in, volume of mixing, the change in volume when two components mix. So when the enthalpy of mixing and volume of mixing goes to 0 or it is equal to 0, then it is an ideal solution. There is one more condition for a solution to be ideal solution. Suppose I take a container. In this container, I have A, I have B. Okay, let A be my solvent. Let B be my solute. There will be an interaction between the solvent-solvent molecules. That is AA interaction. The solvent-solvent molecules have an interaction among themselves. That is AA interaction. Also, the solute particles have a interaction between themselves or among themselves. That is BB interaction. BB interaction. Fine. The solvent particles have interaction among themselves. That is AA interaction. Solute particles which is used, the solute which is used, those particles have an interaction among themselves, that is BB interaction. This will be equal to AB interaction for an ideal solution. AB interaction means the interaction between solute and solvent. The solute-solute interaction and solvent-solvent interaction will be equal to solute-solvent interaction for an ideal solution. So what are the three conditions for a solution to be ideal? Enthalpy of mixing and volume of mixing should be equal to 0. Fine. And the AA interaction, BB interaction should be equal to AB interaction. Also, PA plus PB, that is the partial pressure, sum of partial pressures of the components should be equal to P naught A chi A plus P naught B chi B. If all these conditions are obeyed by a solution, then it is called an ideal solution. Coming to non-ideal solutions. From the name itself, it's clear that it's not ideal. Non-ideal solution. It's not ideal. If it is not ideal, will it obey Rawls law? If it's not ideal, will it obey Rawls law? Ideal solutions obey Rawls law for sure. Paka. Will non-ideal solutions obey Rawls law? No, non-ideal solutions won't obey Rawls law at any cost. At any cost. Fine. So there are two types of showing disobedience to Rawls law by non-ideal solutions. That is positive deviation from Rawls law. Positive deviation from Rawls law and negative deviation from Rawls law. Deviation means what? A change in value from Rawls law. Okay. So some solutions, when the total vapor pressure of the solution is observed, it will be different from the value of the total vapor pressure calculated by Rawls law, using Rawls law. That is, for some solutions, the observed value of pressure, total vapor pressure, the calculated value will be from Rawls law. For some solutions, the calculated value will be less than observed value. Or we can say that the observed value of Rawls law is greater than the calculated value. Such solutions are called non-ideal solutions showing positive deviation. I have taken a container here. Okay, I have a solution here. I have observed the partial pressure of that solution, and now I've also calculated the partial pressure of that solution using Rawls law. The calculated value is less than the observed value, or we can say that the observed value of the solution is greater than the calculated value. In such a case, we can say that is a non-ideal solution because the value deviates from the calculated value of Rawls law, and that deviation is greater than the calculated value, so it is a positive deviation. Non-ideal solution showing positive deviation. Fine. Non-ideal solution showing positive deviation. For such solutions, PA is we have PA. For ideal solution, we have PA equal to P naught A chi A. Right. For solutions showing positive deviation, that is non-ideal solution, PA will be greater than P naught A chi A. PB will be greater than P naught B chi B, and total vapor pressure will be greater than P naught A chi A, here it is chi A, and plus P naught B chi B. Cool. The opposite of this happens, opposite of all this happens here in the negative deviation side. For a non-ideal solution showing positive deviation, delta H mix, comma, delta V mix, that is enthalpy of mixing and volume of mixing, will be greater than 0. So what happens in the negative deviation side? For a non-ideal solution showing negative deviation, a negative deviation from Rawls law, the delta H mix and delta V mix will be less than 0. Also, we have one more condition to be ideal. What was that? AA interaction, BB interaction equal to AB interaction. In the case of positive deviation, the AA interaction and BB interaction will be greater than AB interaction. Okay, the interaction between A and B, that is solute and solvent, will be less than the interaction between solute-solute particles and solvent-solvent particles. But in the case of negative deviation, okay, AA interaction, AB interaction will be less than, AA interaction, BB interaction will be less than AB interaction. The interaction between solute particles and solvent particles will be greater than the solute-solute interaction, solvent-solvent interaction in the case of negative deviation. AA, BB interaction less than AB interaction in the case of negative deviation. AA interaction, BB interaction greater than AB interaction in the case of positive deviation. So, in the case of positive deviation, it is easy to escape. It is easy to escape the liquid surface because, as you can see, the interaction between solute and solvent is very less. The interlocking between them is very less. So it is easy to evaporate. So the vapor pressure is very high in such conditions in the case of positive deviation. Okay. So solution having negative deviation, that is non-ideal solution having negative deviation, the vapor pressure is very low. Because of what? AB interaction is very high. It is really difficult to escape the liquid surface. Okay, it is really difficult because solute-solvent particle has high interaction. They are interlocked. So we have already discussed what is ideal solution, what is non-ideal solution, what is the positive deviation from Rawls law shown by ideal solution, non-ideal solutions, and what is negative deviation from Rawls law shown by non-ideal solutions. So shall we draw the graph of Rawls law, the positive deviation and the negative deviation for non-ideal solutions? 3 graphs are there. So basically the graphs are told by students, like the graphs are really difficult, not being able to understand, but the graphs are really simple. Let's learn how to do the graph of Rawls law in just 1 or 2 minutes. Fine. First of all, X and Y axis. We are having vapor pressure on the Y axis. Okay, vapor pressure. We have mole fraction on the Y axis. Mole fraction. On the X axis. Okay. We are considering 2 components for a solution. That is component number 1, component number 2. When those components are mixed, it's made into a solution. So let the components be 1 and 2. When x1 in the initial stage it is 0. In the final stage it is 1. Okay. The mole fraction of a component 1 goes from 0 to 1, maximum value 1. The mole fraction of second component, it goes from 1, the peak value, to 0. This is a mole fraction of second component. It is going to 0. Fine, let's draw the graph then. These are the conditions provided. Vapor pressure in the y-axis, mole fraction in the x-axis. We are considering 2 components, 1 and 2. The mole fraction of first component is going from 0 to 1, and the second component, the mole fraction, is going from 1 to 0. Now let's draw the graph. We know that the equation of mole fraction is, the equation of vapor pressure is PA equal to P naught A chi A. Fine. Okay. So when chi 1, the mole fraction of the first component is 0, chi A will be 0. So that PA goes to 0. So I am marking the 0 position here. here. Fine. And in the right hand side, you can see that chi1 goes to 1. Okay, the mole fraction of component 1 goes from 0 to 1. So when chi A is 1, we have Pa equal to P naught A. So let that Pa equal to P naught A, right? Pa be here. Pa be here. Okay, in the 1, we have denoting this as Pa. Now, let's draw this graph. Graph for the component 1 is ready. Now, oh. Now we have the second component, PB, right? PB. When the mole fraction is 1, P naught B, chi B. When mole fraction is 1, PB is equal to P naught, PB equal to P naught B, right? Let P naught B or PB here, be here. PB. PB. Some sort of issues for the pen, okay? Anyways, PB is here. Okay, assume that PB is greater than PA. So that PB is drawn a bit higher than PA. And when chi2, the mole fraction of second component, goes from 1 to 0, right? So in the second condition, mole fraction is 0. And of the second component, chi2 is 0. So PB goes to 0. PB goes to 0. That will be here. Now draw a straight line. Draw a straight line from the PB to 0 and connect these points PA and PB. This is the graph for Rawls law or ideal solution. This is the graph for ideal solution or Rawls law. Now, shall we draw the graph for positive deviation, the non-ideal solutions showing positive deviation from Rawls law and non-ideal solutions showing negative deviation from Rawls law. Positive deviation means all the values are higher than the calculated value from Rawls law, right? Even the enthalpy of mixing, volume of mixing is greater than 0. Even the partial pressure calculated, observed from the non-ideal solution is greater than the calculated value from Rawls law. Even the AA interaction, BB interaction is greater than AB interaction. So everything is greater than the calculated value means how do you draw the graph? Just give a curve higher than the normal line. Okay, here we have this kind of curve and here we have a curve like this. This is the graph for positive non-ideal solution having positive deviation from Rawls law. Now let's see the graph for positive non-ideal solution showing negative deviation from Rawls law. Negative deviation from Rawls law. Just draw a curve in the lower portion of each line. This is the curve for negative deviation, the non-ideal solutions showing negative deviation. Fine. So if you know the graph of Rawls law, if you know the graph of ideal solution, you can easily draw the graph of non-ideal solution showing positive deviation and negative deviation. Fine. In today's session, we have discussed about Dalton's law. What was Dalton's law? I've taken 3 containers. In one container, I've taken a volatile liquid A. In second container, I've taken volatile liquid B. And in third container, I've mixed both volatile liquids A and B. Okay, so the total vapor pressure of that solution will be equal to the vapor pressure or individual vapor pressure of each component. That is the law, Dalton's law. Okay, that is a theorem set by Dalton's law. Fine. Okay, coming to Rawls law. If you know what is partial pressure or vapor pressure of each component, Rawls law says that this will be directly proportional to the mole fraction of that component in that solution. Okay, what was the Rawls law saying for a solution of volatile liquids? I've taken a container, mixed 2 or more volatile liquids. The partial pressure of each component, say A or B or C, it will be directly proportional to the mole fraction of that component in that solution. And the equation we get is Pa equal to P naught A chi A, Pb equal to P naught B chi B. And from that, we have derived an equation for the total vapor pressure. The questions can come like find the total vapor pressure for this, for that, for this, for that. Okay, so you need to use this equation: P1 naught plus P2 naught minus P1 naught O into chi2, mole fraction of second component. And also there is an equation to find the mole fraction of a component in vapor phase, and that was YA equal to YA equal to PA by P naught A. PA by P naught A. YB equal to PB by P naught B. Okay, you know the equation to find PB and PA, that is chi A into P naught A, chi B into P naught B. Fine. We have done a problem, and we have come to know what is ideal solution and non-ideal solution. The ideal solutions are those which obey Rawls law over a range of concentration, and for ideal solutions, enthalpy of mixing, volume of mixing will be equal to 0. The solid-solute interaction and solvent-solvent interaction will be equal to solid-solvent interaction. But for non-ideal solutions, there are many differences from ideal solutions. They don't obey Rawls law. Okay, for those solutions which show greater value for vapor pressure than from the calculated value of vapor pressure which we have got from Rawls law, such deviations are called positive deviations, and such deviations are shown by non-ideal solutions. There are non-ideal solutions that who are showing negative deviation from Rawls law. Okay, such solutions show a observed value for vapor pressure less than the calculated vapor pressure through Rawls law. This is a graph for negative deviation for Rawls law. For positive deviation, you need to draw a curve higher than the normal line connecting PA and PB. Fine. Okay, we have learned about the graph of Rawls law, positive deviation and negative deviation. We have some more topics to be covered in this lesson. Hopefully, we'll complete this chapter in the next part. We'll complete all the chapters of +2 chemistry in 3 or 4 parts itself. Okay, if you're doing further problems, the parts will be increased, number of parts will be increased to 5, 6, etc. Anyways, study the topics which I have taken today, and be prepared for the next session. Till then, bye bye.